This video focuses on the harmonic oscillator as part of our ongoing discussion of the second of the three core model systems we'll study in Chem 112. The first being the particle in a box, the second, the harmonic oscillator, and the third, which will be described in a set of future videos, on the rigid rotor. So when we discuss the harmonic oscillator, already begun in class, we break this topic up into four general parts. In the first part that we've already described, Hooke's law and the classical one-body spring system was described, and the equations of motion describing how that system propagates in time was derived in class. We then looked at two-body systems connected by a spring, and we were able to recast that classical sort of system into an effective one-body Hooke's law system. The third part of our discussion of the harmonic oscillator is to now take lessons learned from parts 1 and 2 and apply them in a quantum mechanical framework using the Schrodinger equation. We started this in class already. In this video, I will outline some of the final take-home messages on the quantum mechanical treatment of the 1D harmonic oscillator. In the next video that I'll post, we'll wrap up the harmonic oscillator discussion by connecting all of these points to the vibrational spectroscopy of diatomic molecules. The learning objectives of the video and of this discussion here are threefold. First, to define what we mean by zero-point energy. Second, to be able to describe the relative energies of eigenfunctions given by different harmonic oscillator quantum numbers V. And then lastly, to describe the key characteristics and properties of quantum mechanical harmonic oscillator eigenfunctions and their associated probability densities. So just to briefly overview what we've already described in class and discussed, we have shown that the harmonic oscillator problem that begins with two bodies connected by a spring can be recast into an effective one-body spring problem that follows Hooke's law. We showed how we can use a displacement variable that I'm calling x on the slide here, where x is equal to the difference between the positions of our two particles 1 and 2, so x2 minus x1, minus some equilibrium distance, L0, where the spring would prefer to be and sits at rest. In the process of casting the two-body spring problem into an effective one-body spring problem, we also have to provide some measure of mass for the body at position x, and that mass is usually denoted by the Greek letter mu, and it's called the reduced mass, which is given by the product of the two masses divided by their sum. We also discussed how the potential energy for this 1D harmonic oscillator system is given by V of x and is equal to 1/2 kx squared, where k is the so-called spring constant, or our force constant, and it is related to the frequency of our vibrating system, either the essentially the periodicity of the time displacement of x, which we call omega. In that case, omega is equal to the square root of k over mu, or in terms of the frequency of cycles, or the cycle frequency, nu, which is 1 over 2 pi times the square root of k over mu. Note that omega and nu are related to each other by 2 pi, okay, by a factor of 2 pi. It's also important to note at this point, as I've said a couple times in class already, that we're going to use nu for our frequency of vibration, but we'll also have a quantum number in a bit here, v. We need to be careful not to confuse v with nu or nu with v. And then the last thing we described in class before moving online was that taking the classical system and moving it into a quantum mechanical framework gives us a Hamiltonian, which has the standard kinetic energy term that we know, and the potential energy term that comes from the classical harmonic oscillator of 1/2 kx squared. The energy is quantized, and we use a quantum number to designate the state we're in, V, and the energy E at state V is given by h bar omega times nu plus 1/2. Again, relating omega with nu, we can also write the energy of state V as h nu times v plus 1/2. The very last thing we did in class then was to draw the potential energy surface, or the 1D curve, shown here in black, draw energy lines, shown in red. We discussed how those energy levels are equally spaced. V, the quantum number, begins at 0 and continues in integer increments to infinity. And we noted that the energy of V equals 0 is not 0. There's an intrinsic non-zero energy at the initial state, which is called the 0-point energy. We also noted as a final point before leaving class last week that the energy increases with increasing number of nodes, just as we saw in the particle in a box. Okay. So let's talk a little more about these eigenfunctions. At the top of the slide here is the expression that is used to show the eigenfunction in the same notation as used in the textbook. A wave function psi sub v, where v again is the quantum number, is a function of x and is given by the product of three terms, n, h, and an exponential at the last term. So the n term is a normalization constant. The expressions for those normalization constants are given in the textbook in chapter 5. The capital H is a function of this term we call alpha, which is given by the square root of k times omega over h bar square times x. And that function h is referred to or is known as a Hermite polynomial. The last term is a Gaussian function. It says the sort of distribution that we know from probability. So we have e to the minus alpha x squared on 2. If you look at table 5.2 on page 170 of Macquarie and Simon, you'll see a listing of some of the first few Hermite polynomials. And so what I've done in the bottom two plots here are to show the wave functions and the probability densities for the first 5 states, the ground state v equals 0 to the fourth excited state v equals 4. If we sort of enlarge the graph of wave functions, again, just some of the key features, v equals 0 is in a non-zero energy. That's the 0-point energy. Our states, or our energies between v equals 0 and v equals 1, and the energy between v equals 1 and v equals 2, v equal 2 and v equal 3, and so on, are all equal. There is not an increasing or decreasing energy gap between successive states. They are all equally spaced in the harmonic oscillator. We see increasing number of nodes as we go up in energy as well, which is, again, similar to what we observe for the particle in a box. A couple of additional features, which I'm highlighting here, are that the wave functions at every state seem to bleed out beyond the point where the total energy and the potential energy are equal. This is a non-classical behavior. In a classical system, when our total energy becomes equal to the potential energy, our kinetic energy must be 0. We would stop moving. We would turn around and head back. That's why, again, I mentioned we discussed the classical particle or harmonic oscillator, rather. Those points where the total energy and the potential energy are equal are referred to as turning points, because the particle reaches the turning point and then turns back, goes through the the equilibrium displacement distance, back to the other turning point, and so on and so forth. But in the quantum mechanical harmonic oscillator system, we note that there is some probability of finding our quantum mechanical particle beyond the classical turning points. If we plot the probability densities, again, this is just psi star psi as a function of x, we see that we still have probability, as we'd expect from the wave functions we saw on the previous slide, but there's probability beyond the classical turning points for all states. And there's one other feature I want to point out, which is somewhat classical in nature. Notice for v equals 2, 3, and 4, we can see that the probability of the wave function being out near the classical turning points is greater than it is on the interior of the potential. And the classical interpretation of that, which seems to still hold in the quantum mechanical harmonic oscillator case, is that as the particle approaches the wall or approaches the edge of the potential, and its total energy approaches that of the potential energy and the kinetic goes down, then the particle slows down and effectively spends more time as it approaches the classical turning point. When it turns around and goes back toward the equilibrium displacement position, its potential energy decreases, kinetic energy increases, and the particle moves through the middle part of the potential a bit faster than it does out at the edges. So as a result, as you see here, and I've drawn lines to show where the relative amplitudes are, you'll see that there's more or higher amplitude in our probability densities out near the classical turning points than there is at the equilibrium displacement position. All right, to just summarize what we've gone over here, we've shown that you can cast a two-body problem into an effective one-body problem, and that when we solve the Schrodinger equation, we get quantized energies and eigenfunctions that are products of Hermite polynomials and a Gaussian function. And then lastly, we saw that our harmonic oscillator wave functions have and agree with some classical expectations and properties, and also exhibit some very important non-classical or quantum mechanical behaviors. So that's the end of this video. In the next video, we'll pick up from this point here and discuss how the quantum mechanical harmonic oscillator model allows us to understand and make predictions about the vibrational spectroscopy of diatomic molecules.